Welcome to the Chill Scientist. With the boom in many quantum and computing company stocks, we thought it would be a great time to do a very deep dive in this topic. The story of quantum and computing begins long before anyone even thought of building a device. It starts with the strange rules of quantum mechanics itself, developed in the early 20th century. At that time, physicists were confronted with experimental results that defied classical intuition. Electrons behaving like waves, atoms emitting light in discrete packets, particles that could exist in two states at once. These discoveries were confusing, unsettling, and often ridiculed, but out of them came the mathematical framework of quantum mechanics, which became the most successful physical theory ever devised. It explained everything from the structure of atoms to the behavior of semiconductors, laying the foundation for modern electronics. Yet in those early decades, almost no one considered the possibility of using quantum mechanics itself as a new kind of computing engine. The leap from physics to information theory came later, and it was seeded by thinkers who were willing to ask unusual questions. In the 1960s and 1970s, computer science was developing rapidly, with advances in algorithms, complexity theory, and the formal limits of what machines could calculate. Meanwhile, physicists were grappling with the conceptual puzzles of quantum measurement and entanglement. The two worlds seemed separate, but a few pioneers began to ask, what if information itself was subject to the laws of quantum physics? Could the bizarre features of superposition and entanglement be harnessed not just for describing the world, but for computation? One of the first major conceptual breakthroughs came in 1981 at a conference organized by MIT physicist Richard Feynman. Feynman pointed out that simulating quantum systems on classical computers was incredibly inefficient. To capture all the possible states of even a modest number of particles, the computational resources required grew exponentially. But nature itself doesn't seem to struggle with this problem. It just computes the outcome effortlessly. Feynman suggested that the only way to efficiently simulate quantum physics might be to build a computer that followed quantum rules itself. This was not yet a design, but it was a radical shift in thinking. Computation could be more powerful if it embraced quantum mechanics rather than avoiding it. Around the same time, Oxford physicist David Deutsch took the idea further. In 1985, Deutsch described what he called the universal quantum computer, a theoretical machine capable of performing any computation that a classical computer could, but also leveraging quantum mechanics for problems where classical machines struggle. He showed that such a device could be described with quantum gates, operations that act on quantum bits, or qubits, much like logic gates act on classical bits. Deutsch's work laid the theoretical foundation for quantum algorithms, opening the door to an entirely new branch of computer science. The field remained largely theoretical for the next decade, but two landmark discoveries in the 1990s electrified researchers. The first was Peter Shor's algorithm, published in 1994. Shor demonstrated that a quantum computer could factor large numbers exponentially faster than the best-known classical methods. This wasn't just a mathematical curiosity. It struck directly at the heart of modern cryptography, which depends on the difficulty of factoring for the security of RSA encryption. Suddenly, quantum computing wasn't just an intellectual exercise. It was a potential disruptor of global cybersecurity. The second breakthrough was Love Grover's search algorithm in 1996. Grover showed that a quantum computer could speed up unstructured searches, reducing the time needed from n steps to roughly the square root of n. While not as dramatic as Shor's exponential speedup, Grover's algorithm demonstrated that quantum computing could bring practical improvements across a range of problems. Together, these results convinced skeptics that quantum computing had unique power, not just in physics, but in computation itself. By the late 1990s, experimentalists began attempting to build actual qubits. These early prototypes were crude, single-trapped ions manipulated with lasers. nuclear spins in molecules controlled by nuclear magnetic resonance, superconducting circuits cooled to near absolute zero. The coherence times, the length of time a qubit could maintain its quantum state, were extremely short, often just microseconds. Gate fidelities were low, and error correction remained a distant dream. Still, proof of principle demonstrations showed that the building blocks of quantum computation were physically realizable, even if fragile. The 2000s and early 2000s saw steady progress, though often at the margins of mainstream computing research. Governments and universities funded small projects, but private industry paid little attention. That began to change as tech giants like IBM, Google, and Microsoft recognized the potential. By the mid-2000s, they were investing heavily in superconducting qubits, ion traps, and exotic approaches like topological qubits. The experimental frontier accelerated, coherence times improved, qubit counts increased, and control systems became more sophisticated. A major milestone came in 2019 when Google announced it had achieved quantum supremacy. Using its 53-qubit Sycamore processor, Google performed a specific sampling calculation in 200 seconds that it claimed would take the fastest supercomputer thousands of years. While critics pointed out that the task itself was contrived and that classical methods could narrow the gap, the demonstration was symbolically important. For the first time, a quantum device had clearly outperformed a classical one on a well-defined problem. This announcement kicked off a wave of interest beyond academia. Investors began to view quantum computing as a serious emerging industry. Startups like IonQ, Rigetti, and Quantum raised hundreds of millions of dollars, some going public via SPAC mergers. Governments launched national initiatives, recognizing quantum as a technology with strategic importance. Suddenly, quantum computing was no longer an obscure corner of physics, but a global race, often described as the space race of the 21st century. That brings us to the present, where quantum computing sits at a fascinating crossroads. On one hand, no one has yet built a machine capable of solving useful, real-world problems better than classical supercomputers. On the other hand, progress is undeniable. Qubit counts are rising, fidelities are improving, and error correction experiments are scaling up. Companies differ on when they expect practical quantum advantage to arrive, with predictions ranging from a few years to several decades. Meanwhile, the financial markets have taken notice. Stocks of companies like IonQ have surged at times, riding waves of enthusiasm about quantum's potential. Investors see quantum as both a technology play and a long-term bet on reshaping industries from cybersecurity to pharmaceuticals. The valuations of some companies are already high relative to their revenues, sparking debates about whether this is the beginning of a genuine technological revolution or the early stages of a hype-driven bubble. The origins of quantum computing, then, are not just a tale of physics, but of human imagination, ambition, and risk-taking. From Feynman's thought experiments to Deutsch's universal quantum machine, from Shor's cryptography-shattering algorithm to Google's supremacy claim, each step reflects both scientific insight and a willingness to dream big. Today's researchers, engineers, and investors are building on those foundations, knowing that the rewards could be transformative or that the challenges could prove insurmountable. Part 2. To understand why quantum computers are different from classical ones, we need to start with the fundamental unit of information, the bit. In a conventional computer, the kind sitting on your desk, in your phone, or inside a data center, a bit is the most basic building block. It can be in one of two states, 0 or 1. All of modern computing, from word processors to video games to artificial intelligence, ultimately boils down to manipulating billions or trillions of these zeros and ones using electrical signals. The power of classical computers comes from their scale, tiny transistors etched onto chips, switching billions of times per second, coordinating to process immense amounts of information. Quantum computing introduces something new, the qubit, or quantum bit. Unlike a classical bit, which can only be in state 0 or 1, a qubit can exist in a superposition of both states at the same time. Mathematically, you can think of it as a weighted combination of 0 and 1, with probabilities attached to each. When you measure a qubit, you only ever see one outcome, either 0 or 1. But until that measurement, it behaves as if it occupies both simultaneously. This idea of superposition is one of the strangest and most powerful features of quantum mechanics. To see why this matters for computing, imagine a single classical bit. It can store one of two possibilities, 0 or 1. A qubit, in superposition, encodes both possibilities at once. Now scale up. Two classical bits can store one of 4 possible states, but only one at a time. 2 qubits in superposition can represent all 4 states at once. With 3 qubits, you can represent 8 states simultaneously. With 20 qubits, over 1 million states are possible. With 50 qubits, you're already beyond what the largest supercomputers can directly simulate. The growth is exponential, and it comes from this ability of qubits to explore multiple possibilities in parallel. But superposition is only part of the story. The second key ingredient is entanglement, another uniquely quantum phenomenon. When qubits become entangled, their states are linked in a way that defies classical intuition. Measuring one immediately affects the state of the other, even if they're far apart. Einstein famously called this spooky action at a distance. In a quantum computer, entanglement allows qubits to share information in ways classical bits cannot. It creates correlations that enable certain algorithms to perform operations exponentially faster than their classical counterparts. Without entanglement, quantum computers would not outperform classical ones in meaningful ways. Then there's interference, the third crucial property, because qubits can exist in superpositions with different amplitudes, the weights attached to 0 and 1. Those amplitudes can interfere with each other like waves on water. By carefully designing quantum algorithms, scientists set up constructive interference to amplify correct solutions and destructive interference to cancel out incorrect ones. This wave-like behavior is what makes algorithms like Shor's and Grover's possible. It's also why quantum programming is very different from classical programming. You're not just moving bits through logic gates, you're choreographing probability waves. Of course, none of this comes for free. The same quantum properties that give qubits their power also make them fragile. A classical bit stored as an electrical charge on a transistor is stable. It stays 0 or 1 until deliberately changed. A qubit, by contrast, is easily disturbed by its environment. Tiny amounts of heat, stray electromagnetic radiation, or even slight vibrations can cause a qubit to lose its quantum state, a process called decoherence. Once decoherence sets in, the superposition collapses and the qubit becomes useless for computation. That fragility is why quantum computers must operate under extreme conditions. Superconducting qubits, for example, need to be cooled to near absolute zero using dilution refrigerators. Trapped ion qubits require ultra-high vacuum chambers and precisely tuned lasers. Neutral atom qubits are held in place by arrays of optical tweezers, each controlled with incredible precision. Photonic qubits require single photon sources and ultra-sensitive detectors. In every case, the engineering challenge is not just creating a qubit, but keeping it coherent long enough to perform useful calculations. Another challenge comes from error rates. Classical bits are remarkably reliable. Modern chips have error rates so low that engineers rarely think about them outside of specialized systems. Qubits, however, are noisy. Even the best systems today achieve gate fidelities, the accuracy of quantum operations, of around 99.9%, which sounds high until you realize that thousands or millions of gates may be needed for a single algorithm. Without error correction, small mistakes accumulate rapidly, overwhelming the calculation. Quantum error correction is one of the most important and difficult areas of research in the field. The idea is to use multiple physical qubits to encode a single logical qubit that is more stable. By detecting and correcting errors in real time, logical qubits can survive much longer than individual physical qubits. The catch is that error correction requires huge overhead. Depending on the code used, it might take hundreds or even thousands of physical qubits to create just one. Error-corrected logical qubit. This is why building machines with millions of physical qubits is often cited as the threshold for truly useful, fault-tolerant quantum computing. The comparison between bits and qubits is sometimes framed in terms of brute force versus elegance. Classical computers are incredibly powerful because they manipulate vast numbers of bits very quickly. Quantum computers, if built at scale, would achieve their power not by brute force, but by harnessing the subtle rules of quantum mechanics. They won't replace classical machines for everything. In fact, for most tasks, classical computers will remain better. Instead, quantum computers are specialized tools designed for problems where superposition, entanglement, and interference give them unique advantages. Consider factoring large numbers, the task that Shor's algorithm targets. A classical computer has to essentially test many possible factors with optimizations, but still facing exponential growth in difficulty. A quantum computer, by leveraging interference patterns, can zero in on the correct factors much faster. Or think about simulating molecules. A classical machine must keep track of an exponentially growing number of states, but a quantum computer can represent them naturally because it follows the same quantum rules. These are the kinds of problems where qubits show their worth. It's important to stress that not every problem benefits from quantum computing. Running your web browser or playing a video game will never require qubits. Classical chips excel at those tasks. The promise of quantum is targeted: chemistry, materials science, cryptography, optimization, and certain machine learning tasks. For everything else, classical computing will remain dominant. This distinction matters because it frames quantum computers not as replacements, but as accelerators or complements to classical infrastructure. Over the years, researchers have explored many different physical systems for realizing qubits, each with its trade-offs. Superconducting qubits are fast and relatively easy to fabricate, but decoherence times are short. Trapped ions are slow but extremely stable. Neutral atoms scale well, but still face challenges in gate fidelity. Photonic qubits travel long distances without decohering, making them attractive for networking. But building large-scale processors remains difficult. Topological qubits, still hypothetical, promise built-in error protection, but have yet to be realized experimentally. This diversity reflects the fact that no one knows which path will ultimately succeed, or whether multiple approaches will coexist. The qubit, then, is both the source of quantum computing's potential and its greatest obstacle. Its unique properties, superposition, entanglement, interference, enable computations beyond the reach of classical machines. Yet those same properties make it delicate, noisy, and hard to scale. The entire industry revolves around finding ways to harness qubits reliably, whether through better materials, improved control systems, or clever error correction. Until that problem is solved, quantum computing will remain a tantalizing promise rather than a practical tool. Understanding the difference between bits and qubits is the foundation for everything else in this field. It explains why quantum computers are not just faster classical machines, but something entirely different, built on a new paradigm of physics. It also explains why progress is measured, not just in the number of qubits, but in their quality, stability, and connectivity. Each advance in qubit technology brings us closer to a future where quantum computers can tackle problems we can only dream of solving today. Part 3. The leap from theory to experiment in quantum computing was anything but straightforward. In the 1980s and early 1990s, physicists could describe qubits mathematically, but building one in the lab seemed almost impossible. The properties of quantum mechanics that make qubits powerful, superposition, entanglement, and interference, are also notoriously fragile. For years, the idea of a working quantum computer remained closer to science fiction than engineering reality. Still, researchers persisted, and the first prototypes emerged in unexpected forms. One of the earliest demonstrations came from nuclear magnetic resonance, or NMR. This technique, which had been used for decades in chemistry and medical imaging, as MRY, relies on the spins of nuclei in molecules. In the late 1990s, scientists realized that these nuclear spins could act as qubits. By applying carefully tuned radio frequency pulses, they could manipulate the spins into superpositions and even entangle them. NMR systems demonstrated small-scale quantum algorithms, including simplified versions of Shor's algorithm. These experiments were important because they proved that real physical systems could implement quantum logic gates. However, NMR qubits were not scalable. They relied on ensembles of molecules, and controlling large numbers individually was impossible. Still, NMR gave the world the first working quantum computers, however limited they were. At the same time, other groups were experimenting with trapped ions. In this approach, individual atoms are held in place using electromagnetic fields inside a vacuum chamber. Lasers are then used to cool the ions to near absolute zero and manipulate their internal states. Because atoms are naturally identical, ion qubits are remarkably stable and uniform. Early trapped ion experiments in the 1990s demonstrated the ability to create and measure single qubits with high fidelity. By the early 2000s, researchers showed entanglement between pairs of ions and implemented simple 2-qubit gates. These were critical milestones because entangling operations are the backbone of quantum computation. Trapped ions quickly gained a reputation for their precision and long coherence times, though their scaling challenges were apparent from the beginning. Superconducting qubits were another avenue explored in the 1990s. These devices use circuits made from superconducting materials cooled to millikelvin temperatures. In certain configurations, the current in these circuits can behave quantum mechanically, with quantized energy levels that act as qubit states. Early superconducting qubits were crude and unstable, decohering in nanoseconds. But steady improvements in fabrication techniques and circuit design extended coherence times into microseconds, then milliseconds. Unlike trapped ions, which rely on atomic physics, superconducting qubits could be manufactured using microfabrication processes similar to those used in the semiconductor industry. This gave them scalability potential, even if the devices were noisy at first. Photonic qubits also attracted attention in the early days. Photons, or particles of light, are naturally resistant to decoherence because they interact weakly with their environment. This makes them ideal carriers of quantum information, especially for communication. Researchers demonstrated entangled photon pairs, quantum teleportation, and basic quantum gates using optical setups. However, building large-scale photonic quantum computers required reliable single-photon sources and detectors, which were difficult to engineer at the time. As a result, photonics was often used for quantum communication experiments rather than computing. These different approaches each produced prototypes, and while none was anywhere near useful for solving real problems, they established the experimental foundation of the field. The early 2000s saw steady progress. Small systems of 2, 3, or 5 qubits were demonstrated. Algorithms like Grover's search were tested on a tiny scale, and decoherence times improved incrementally. These experiments also revealed just how hard the challenge would be. Controlling even a handful of qubits required specialized equipment: vacuum chambers, ultra-stable lasers, dilution refrigerators, or complicated optical setups. Scaling from 5 qubits to 50 was not a matter of just adding more. It meant entirely rethinking architectures. A key theoretical breakthrough during this period was the development of quantum error correction codes. In 1995, Peter Shor and Andrew Steen independently showed that it was possible to protect quantum information from errors by spreading it across multiple physical qubits. This was a profound result because many had assumed quantum error correction was impossible. Measurement destroys quantum states. So how could you detect and fix errors without collapsing the computation? The answer was clever encoding. Instead of storing information in one fragile qubit, it would be distributed across many, with redundancy allowing errors to be detected indirectly. This meant that fault-tolerant quantum computing was possible in principle, even if the overhead was enormous. From then on, error correction became a central part of experimental research. By the late 2000s, small-scale demonstrations of error correction were appearing in labs. Scientists showed that they could detect and correct single-bit errors using codes like the 3-qubit bitflip code or more advanced surface codes. These experiments were slow and resource-intensive, but they proved that error correction was not just theory. They also highlighted the sheer scale required for fault tolerance. Millions of physical qubits for thousands of logical qubits. This realization pushed experimentalists to focus not only on building more qubits, but on making them higher quality, with longer coherence times and lower error rates. During this period, different approaches began to coalesce into distinct schools of quantum hardware. Ion trap researchers emphasized precision and stability. Superconducting researchers emphasized scalability and integration, and photonic researchers emphasized communication and networking. Each camp acknowledged the others but argued for the superiority of their own path. Microsoft, meanwhile, pursued an exotic direction: topological qubits, which we'll revisit later. These debates were, and still are, intense, because the choice of hardware platform determines the trajectory of the entire field. By the early 2000s, prototypes were becoming more sophisticated. Trapped ion systems demonstrated entanglement among multiple ions and high-fidelity gates. Superconducting systems achieved coherence times long enough to run small algorithms. Photonic experiments showed multi-photon entanglement and simple quantum circuits. Governments and funding agencies began to take notice, launching initiatives to support larger-scale projects. The race to demonstrate useful quantum computing was beginning in earnest. One of the defining features of this era was the shift from proof-of-principle demonstrations to engineering roadmaps. Instead of just showing that qubits could exist, researchers began to ask, how can we scale this up? What kind of control electronics are needed? How do you connect qubits efficiently? What kind of error correction codes are practical? This transition marked the maturation of the field. It was no longer a collection of physics experiments, but a multidisciplinary engineering challenge involving materials science, cryogenics, optics, and computer science. Looking back, the early experiments might seem primitive. A handful of qubits running toy algorithms in tightly controlled labs are far removed from the vision of million-qubit machines tackling chemistry, finance, or artificial intelligence. But those first steps were essential. They proved that the rules of quantum mechanics could be harnessed for computation in real devices. They showed that error correction, once thought impossible, was achievable in principle. And they laid the groundwork for the rapid acceleration that followed when big tech companies and investors entered the field in the 2010s. Today's quantum computers, with dozens or even hundreds of qubits, trace their lineage directly to those early prototypes. Every trapped ion chain, superconducting chip, or photonic circuit is built on decades of incremental progress, each experiment solving a small part of the larger puzzle. Without those first fragile qubits, there would be no quantum industry today. Part 4. By the early 2000s, quantum computing had grown from a niche area of physics research into a global competition. Theoretical breakthroughs and small-scale experiments had convinced enough people that the technology was possible in principle, but no one yet knew how to make it practical. At this point, some of the biggest technology companies in the world decided to step in. With their money, infrastructure, and global influence, the field entered what many call the first quantum race. IBM was one of the earliest corporate giants to commit seriously. The company had a long history in computing innovation, from mainframes to supercomputers, and it saw quantum as the next frontier. Around 2016, IBM launched its Quantum Experience platform, allowing researchers and the public to access small, superconducting processors through the cloud. This was a turning point. Instead of quantum computing being locked away in physics labs, anyone could experiment with real qubits from their laptop. It democratized access, built a developer community, and signaled that IBM was serious about leading the field. IBM also laid out detailed roadmaps, projecting future chip sizes, error rates, and architectures. This kind of transparency gave the company credibility, and it has largely delivered on its milestones, from a 5-qubit chip in 2016 to devices with hundreds of qubits today, with a roadmap that extends into the thousands. Google entered the race from a different angle. In 2014, it hired John Martinis, a physicist who had been a pioneer in superconducting qubits, and set up a quantum hardware lab in Santa Barbara. Google aimed not just to build qubits, but to make headlines. In 2019, it announced that its 53-qubit Sycamore processor had achieved quantum supremacy. The team performed a highly specialized sampling calculation in about 200 seconds, which they claimed would take the fastest supercomputer thousands of years. Although the practical usefulness of the task was debated, the symbolic impact was huge. Google had demonstrated that a quantum computer could outperform classical hardware on a well-defined problem. The announcement was covered worldwide, and it ignited excitement and controversy about how close we were to useful quantum computing. Microsoft took yet another path. While IBM and Google focused on superconducting qubits, Microsoft pursued a more exotic approach: topological qubits. The idea was that if you could encode information in special quasi-particles called Majorana modes, the resulting qubits would be naturally resistant to errors. In theory, this would make building a large-scale, fault-tolerant computer much easier. But while elegant on paper, the physics has been extraordinarily difficult to realize. For years, Microsoft announced progress, only to retract or revise results when evidence didn't hold up. Despite setbacks, Microsoft continued to invest heavily, funding labs and positioning its Azure Quantum Cloud service as a way to stay relevant in the short term. Unlike IBM and Google, which could show tangible machines, Microsoft's quantum division was betting on a high-risk, high-reward future. While IBM, Google, and Microsoft became the most visible players, others were also important. Intel invested heavily in superconducting research and spin qubits, leveraging its semiconductor expertise. Rigetti, a startup founded in 2013, tried to compete with the giants by building superconducting chips and offering them via the cloud. Although smaller, Rigetti's agility and willingness to experiment gave it a niche in the ecosystem. Around the same time, D-Wave, a Canadian company, was selling quantum annealers, special-purpose machines optimized for optimization problems. While not universal quantum computers, D-Wave systems had thousands of qubits and attracted customers in logistics, finance, and defense. The rise of these players transformed quantum computing into more than just a scientific field. It became a strategic industry, attracting government funding and international competition. The US, China, and the European Union launched billion-dollar initiatives, viewing quantum as critical for national security and economic leadership. Governments feared a scenario where another country achieved practical quantum computing first, potentially breaking cryptographic systems or gaining advantages in science and defense. What had once been academic curiosity was now part of geopolitics. Each of the big players chose a slightly different strategy. IBM emphasized openness, building a global community around its hardware and publishing a transparent roadmap. Google, emphasized breakthrough demonstrations, aiming for high-profile milestones like quantum supremacy. Microsoft emphasized long-term vision, betting on topological qubits while keeping itself visible with cloud services. Intel emphasized engineering rigor, focusing on manufacturability and leveraging its fabrication plants. Rigetti emphasized accessibility, trying to carve out space as the startup alternative. And D-Wave emphasized commercial traction, selling machines that could already tackle niche problems. The first quantum race wasn't just about hardware, it was also about software, ecosystem, and talent. IBM developed Qiskit, an open-source software framework that allowed developers to write and run quantum programs. Google contributed Cirq, aimed at researchers. Microsoft developed QNumber, a new programming language for quantum algorithms. Rigetti launched Forest, its own toolkit. These software ecosystems were critical because they trained a new generation of developers and researchers. If quantum computers were going to be useful, they needed people who knew how to use them. Building that community early was a strategic advantage. This period also saw the beginning of partnerships between big tech companies and traditional industries. IBM partnered with J.P. Morgan Chase to explore quantum algorithms for finance, with ExxonMobil for chemistry, and with Daimler for battery research. Google collaborated with NASA and academic institutions. Microsoft partnered with universities and startups to build its Azure Quantum Network. These partnerships were often more about learning and positioning than immediate results, but they signaled that quantum was moving into the broader economy. The competition between IBM and Google in particular highlighted the different philosophies. IBM criticized Google's supremacy claim, arguing that the problem could be solved on classical machines faster than Google suggested. IBM also argued that the term quantum supremacy was misleading and preferred the term quantum advantage, which emphasizes practical usefulness rather than symbolic demonstrations. Google, for its part, defended its achievement as proof that quantum computing had crossed a fundamental threshold. The debate underscored the tension between hype and realism, a tension that still defines the field today. By the mid-2000s to early 2000s, the quantum landscape had changed completely. What started as small academic labs tinkering with fragile qubits had become a global race involving trillion-dollar corporations, billion-dollar government programs, and startups flush with venture capital. Each player staked its position with a different vision, but all were united by the belief that quantum computing could eventually transform industries. The first race was less about who would build a practical machine immediately, and more about who would define the ecosystem, attract the talent, and secure the trust of governments and investors. Looking back, this era was as much about perception as progress. IBM's roadmaps gave a sense of inevitability. Google's supremacy experiment grabbed global headlines. Microsoft's topological gamble inspired debate, and D-Wave's annealers kept the idea of commercial quantum computing alive, even if in a limited form. Together, these moves established quantum computing as one of the defining technological competitions of the 21st century. Part 5. The mid-2000s to early 2000s didn't just belong to the big tech giants. In fact, some of the most ambitious claims and daring experiments came from startups that emerged to challenge IBM, Google, and Microsoft. These smaller companies, often spun out of university labs, promised not just incremental progress, but radical breakthroughs. Unlike the tech titans, they were built from the ground up with quantum as their sole mission. Their founders pitched themselves as the future Googles of quantum computing and convinced investors to pour in hundreds of millions of dollars, sometimes billions. The result was an explosion of companies, each betting on a unique path towards scalable quantum computing. One of the most talked about was IonQ. Founded in 2015 by Chris Monroe and Young-Sun Kim, IonQ built on years of research in trapped ion systems. Instead of superconducting circuits or photonic chips, IonQ's machines trapped individual ytterbium ions in electromagnetic fields and manipulated them with lasers. The company argued that trapped ions had natural advantages. They were identical, had long coherence times, and offered high-fidelity gates. In practice, IonQ demonstrated some of the highest quality qubits in the industry, even if scaling them up was tricky. What made IonQ particularly visible was its decision to go public in 2021 through a SPAC merger. Suddenly, it wasn't just an academic spinout. It was a publicly traded company with billions in market capitalization. Investors saw IonQ as a pure play on quantum computing, and its stock price fluctuated wildly as hype and skepticism collided. IonQ positioned itself as a long-term bet, arguing that while others rushed to add qubits, its focus on quality and error correction would eventually pay off. Another major startup story was PsiQuantum, founded in 2016 in Silicon Valley. Instead of ions or superconducting circuits, PsiQuantum staked everything on photonics. Its founders, Jeremy O'Brien and Terry Rudolph, believed that photons were the best qubits because of their stability and potential for scalability. The company's bold claim was that it could build a 1 million qubit quantum computer using existing semiconductor manufacturing processes. While others struggled to scale to 50 or 100 qubits, PsiQuantum was talking about millions. It attracted massive investment, over $1 billion, despite the fact that it had yet to publicly demonstrate a working quantum computer. Instead, PsiQuantum operated in stealth, working with global foundries to fabricate photonic chips and insisting that large-scale quantum computing was achievable within the decade. Its confidence, combined with secrecy, made it one of the most intriguing and polarizing players in the field. Xanadu, based in Toronto, was another startup pushing photonics, but in a very different style. Founded in 2016, Xanadu quickly gained a reputation for openness. It released Penny Lane, an open-source software framework for quantum machine learning that integrated quantum computing with AI workflows. While PsiQuantum stayed quiet, Xanadu was loud and community-driven. Its photonic hardware used squeezed light sources and innovative detection methods. In 2021, Xanadu announced Borealis, a photonic machine that set records for Gaussian boson sampling, a specialized task that, like Google's supremacy experiment, was designed to demonstrate quantum advantage. Xanadu's approach stood out not only for its technical direction, but also for its integration of software and hardware. It wasn't just building chips. It was building tools for developers to start experimenting with hybrid quantum classical algorithms. Quantinuum was born from the merger of Honeywell Quantum Solutions and Cambridge Quantum in 2021. Honeywell had quietly been building one of the most advanced trapped ion platforms, while Cambridge Quantum was a leader in quantum software, particularly quantum chemistry and cryptography. By combining the two, Quantinuum positioned itself as a vertically integrated quantum powerhouse. Its trapped ion machines consistently ranked among the highest performing in benchmark tests, and its software tools gave it immediate relevance for customers. Unlike many startups, Quantinuum had the backing of a major industrial player, giving it stability and credibility. Its focus on both hardware and software made it one of the few companies able to serve enterprise clients directly with quantum applications, even at the current limited scale. Infleqtion, formerly known as Cold Quanta, was another ambitious entrant. Based in Boulder, Colorado, the company specialized in cold atom technology. Instead of superconducting circuits or photonic chips, Infleqtion used clouds of neutral atoms cooled to near absolute zero and controlled with lasers. This approach offered a different balance of trade-offs. Neutral atoms could be arranged in scalable arrays, and their interactions could be tuned to perform computations. Infleqtion also had one of the broadest portfolios in quantum technology, spanning computing, sensing, and communications. By not limiting itself to just one application, it positioned itself to benefit from multiple quantum markets. The rebranding to Infleqtion in 2022 emphasized its ambition to be a central player in the broader quantum ecosystem. These companies represented a second wave of the quantum race, one driven by startups rather than tech giants. What they shared was boldness. IonQ promised the best quality qubits. PsiQuantum promised the largest scale. Xanadu promised openness and integration with AI. Quantinuum promised end-to-end solutions. Infleqtion promised versatility across quantum technologies. Each of them attracted significant investment, often before delivering fully on their technical claims. For investors, this was a high-risk, high-reward game. If even one of these companies succeeded, the payoff could be enormous. The rise of startups also fueled competition in business models. Some, like IonQ and Rigetti, chose to go public early, giving retail investors direct exposure to quantum. Their stock prices became proxies for the hype cycle, soaring on news and plunging on delays. Others, like PsiQuantum, remained private but commanded sky-high valuations from venture capital. Quantinuum leveraged its corporate backing to pursue partnerships with clients in chemistry and pharmaceuticals. Xanadu leaned heavily into its software ecosystem, appealing to researchers and AI developers. Infleqtion spread its bets across multiple quantum markets, hedging against the long timeline for computing. Startups also contributed to shaping public perception of quantum computing. Headlines about PsiQuantum's million-qubit plans or IonQ's claims of leading performance helped fuel excitement and skepticism. Critics pointed out that many promises were decades away from realization, if at all. Supporters argued that ambition was necessary, and that without bold claims, the field would never attract the investment it needed. This dynamic mirrored earlier technological revolutions, where hype and skepticism coexisted, and only time sorted out which companies would endure. What distinguished this period from earlier eras was the sheer diversity of approaches. While the big players were mostly focused on superconducting or ion trap systems, startups expanded the field to include photonics, neutral atoms, and hybrid architectures. This diversity was healthy for the industry, ensuring that no single approach dominated too early. It also created a race not just between companies, but between fundamentally different visions of what a quantum computer should look like. By the early 2020s, the quantum startup ecosystem had matured into an essential part of the industry. Governments, corporations, and investors began to treat these companies as serious contenders, not just speculative ventures. Some had real revenue streams, others had strong partnerships, and all had ambitious roadmaps. Whether or not they would deliver on their promises remained uncertain, but one thing was clear. The race to build the first practical quantum computer was no longer limited to a handful of tech giants. The startups had entered the arena, and they were playing to win. Part 6. Grover's Algorithm. As the number of players in quantum computing grew, so too did the diversity of approaches. Unlike classical computing, where silicon-based transistors emerged as the dominant standard early on, quantum computing remains a landscape with multiple contenders, each with its own advantages, disadvantages, and engineering challenges. The hardware itself is the heart of the race, because every quantum algorithm, software framework, and business model ultimately depends on what kind of qubits exist and how they perform. Superconducting qubits are the most prominent, largely because of the resources behind them. Companies like IBM, Google, Rigetti, and Intel have invested billions into superconducting technology. These qubits are built from tiny electrical circuits made of superconducting materials, cooled to just a few thousandths of a degree above absolute zero. At these temperatures, the circuits behave quantum mechanically, with quantized energy states that can represent qubit values. Superconducting qubits have several key strengths. They can be fabricated using methods similar to those used in the semiconductor industry. They can be integrated into chips with dozens or even hundreds of qubits, and they can perform operations very quickly on the order of nanoseconds. This speed is valuable because it allows many operations to be performed before decoherence sets in. The weaknesses are equally important. Superconducting qubits are relatively noisy compared to other platforms, with error rates typically higher than trapped ions. They also require extremely complex cryogenic setups, including dilution refrigerators that cost millions of dollars and can only be operated by specialists. Scaling to thousands or millions of qubits requires not only making larger chips, but also engineering control electronics that can manage enormous numbers of signals at near zero temperatures. Despite these challenges, superconducting qubits have made some of the most publicized advances, including Google's quantum supremacy experiment and IBM's steadily growing processors. Trapped ion qubits take a completely different approach. Instead of circuits, they use individual atoms suspended in electromagnetic fields inside ultra-high vacuum chambers. Lasers are then used to cool, manipulate, and entangle the ions. Because atoms are identical by nature, trapped ion qubits have extremely high fidelity, meaning they can maintain coherence for much longer than superconducting qubits. Operations on trapped ions are slower, microseconds or milliseconds instead of nanoseconds, but the stability often makes up for it. Another major advantage is connectivity. Any ion in a chain can, in principle, interact with any other, reducing the complexity of circuit layout compared to superconducting chips, where qubits usually only interact with their nearest neighbors. Scaling trapped ion systems is challenging in different ways. While a few dozen ions can be held in a single trap, going beyond that becomes difficult because the ions start to interact in unwanted ways. To scale further, engineers must build architectures where multiple traps are linked together, often using photonic interconnects. Companies like IonQ and Quantinuum argue that this modular approach can eventually scale to very large systems, but it requires enormous progress in laser control, vacuum engineering, and photonic networking. Photonics, the focus of companies like PsiQuantum and Xanadu, takes yet another path. Instead of atoms or circuits, photons themselves act as qubits. Photons are ideal carriers of quantum information because they rarely interact with their environment, giving them naturally long coherence times. They are also fast, traveling at the speed of light, and can be transmitted over long distances, making them attractive for quantum networking. Photonic quantum computing usually encodes information in properties such as polarization or phase of light. The biggest challenge for photonics is control. Reliable single photon sources and detectors are difficult to engineer, and the probability of two photons interacting in a controlled way is extremely low. To get around this, researchers rely on probabilistic methods and error correction schemes that require huge overhead. PsiQuantum's argument is that by leveraging semiconductor manufacturing processes, it can build enormous photonic circuits that compensate for these inefficiencies and still reach 1 million qubits. Xanadu takes a slightly different path with squeezed states of light and continuous variable quantum computing. While photonics has not yet demonstrated as many small-scale algorithms as superconducting or trapped ion systems, its potential scalability keeps it in the race. Neutral atom qubits, the specialty of Infleqtion and other emerging companies, use arrays of atoms cooled to near absolute zero and trapped with lasers, but without the strong electromagnetic fields of ion traps. One advantage is scalability. Neutral atoms can be arranged in large grids using optical tweezers, allowing hundreds of qubits to be manipulated at once. Their interactions can be controlled by exciting them into Rydberg states, where atoms become highly responsive to each other. This tunability makes them promising for both computation and quantum simulation. Neutral atoms also avoid some of the complexity of ion traps, though they still require sophisticated laser systems and cryogenic environments. While younger as a field, neutral atoms have rapidly gained attention for their scalability potential. Topological qubits represent perhaps the most exotic approach. Pursued most notably by Microsoft, they rely on the idea that certain quasi-particles, called Majorana modes, could encode information in a way that is inherently resistant to local noise. In theory, topological qubits would be far more stable than other types, dramatically reducing the need for error correction. The catch is that no one has yet demonstrated a stable topological qubit in practice. The physics is extraordinarily difficult, requiring special materials and extremely fine control. For over a decade, Microsoft has reported progress and then revised its claims after further scrutiny. While topological qubits remain speculative, their promise is so great that some researchers continue to pursue them as the holy grail of fault-tolerant quantum computing. Each approach has trade-offs that reflect deeper questions about the future of the field. Do we prioritize speed, as with superconductors, stability, as with trapped ions, scalability, as with photonics and neutral atoms? Or do we hold out hope for a fundamentally better qubit, as with topological approaches? The answer may not be one size fits all. Some experts believe the future will involve hybrid systems, where different types of qubits are linked together for different tasks. For example, superconducting qubits might be used for fast operations, while photonics provides long-distance communication, and trapped ions handle memory. The hardware race is not just about physics, but about engineering and economics. Superconducting systems benefit from existing semiconductor fabrication infrastructure. Trapped ions benefit from atomic physics expertise and precision optics. Photonics benefits from the telecom industry's investments in lasers and fiber optics. Neutral atoms benefit from advances in cold atom physics. Topological approaches depend on breakthroughs in condensed matter physics and materials science. Each ecosystem has its own strengths, weaknesses, and funding networks. As of today, no clear winner has emerged. Superconducting and trapped ion systems are furthest along in terms of running real algorithms, but they face scaling challenges. Photonics and neutral atoms are less mature, but potentially more scalable. Topological qubits remain theoretical. The diversity of approaches keeps the field dynamic and ensures that progress is not locked into one path too early. It also makes comparisons difficult. A 100-qubit superconducting chip may not be directly comparable to a 20-qubit trapped ion system or a photonic experiment with thousands of modes. Metrics like gate fidelity, connectivity, and error correction overhead matter as much as raw qubit counts. The competition between hardware platforms reflects the broader uncertainty of quantum computing's future. Each company is betting on a different vision of what the first practical quantum computer will look like. Investors and researchers alike are watching to see which path pays off. Just as the early days of classical computing saw vacuum tubes, transistors, and magnetic cores compete before silicon transistors became dominant, the quantum era is still in its Wild West phase. It may be years, even decades, before the industry converges on a standard. Until then, the diversity of hardware approaches is both a challenge and a strength, driving innovation from multiple directions at once. Part 7. Error correction. If there is one obstacle that defines the quantum computing race more than any other, it is error correction. Quantum systems are notoriously fragile. Every qubit is subject to decoherence, where information leaks into the environment, and to operational errors when gates are applied. Unlike classical bits, which can be refreshed and protected relatively easily, quantum states cannot be copied due to the no-cloning theorem. This makes error correction an extraordinarily difficult problem, and yet, without it, practical quantum computing is impossible. The origins of quantum error correction go back to the mid-1990s. Peter Shor, who had already stunned the world with his factoring algorithm, showed that it was theoretically possible to detect and correct errors in quantum information without measuring away the very states you were trying to protect. Around the same time, Andrew Steen developed alternative codes with similar properties. The essential trick was to spread information across multiple physical qubits in such a way that errors could be inferred indirectly. For example, Instead of storing a single logical qubit in one physical qubit, you would store it in 7 or 9. By measuring special syndrome qubits, you could tell whether an error had occurred and correct it without collapsing the underlying quantum information. The mathematics was elegant, but the implications were daunting. Error correction required massive overhead. To make just one reliable logical qubit, you might need hundreds or thousands of physical qubits. This was discouraging because even the best labs could only control a handful of qubits at the time. Still, the result was revolutionary. It showed that quantum computing was possible in principle. It was no longer doomed to be wiped out by noise as soon as systems grew larger. As experimental platforms improved in the 2000s and 2010s, researchers began demonstrating error correction in the lab. Early experiments showed that simple codes could detect and sometimes correct bit flip or phase flip errors. More advanced experiments implemented the surface code, which became the most promising candidate for scalable error correction. The surface code arranges qubits on a two-dimensional grid and uses nearest neighbor interactions to check for errors. Its major advantage is that it only requires local interactions, which are easier to engineer in real hardware. The trade-off is that the overhead is immense. Estimates suggest that building a useful quantum computer with surface codes would require millions of physical qubits. Despite the scale, the surface code has become the gold standard because it appears to be within reach of current architectures. Superconducting and trapped ion platforms, in particular, have been working toward demonstrating logical qubits with error correction. The milestone researchers are aiming for is known as the break-even point, when a logical qubit protected by error correction is more reliable than the underlying physical qubits it is built from. This hasn't been achieved universally yet, but in 2023, Google reported experimental progress where a logical qubit encoded in 49 physical qubits maintained coherence longer than the individual qubits themselves. It was a sign that break-even might be achievable in the near future. Other codes are also being studied. Color codes, concatenated codes, and bosonic codes each have unique properties. Bosonic codes, for instance, use the states of oscillators, such as microwave resonators, to encode quantum information in more error-resistant ways. Some platforms find these attractive because they can reduce the overhead required compared to surface codes. Researchers are constantly searching for codes that balance practicality with protection. The challenge is not only theoretical, but also deeply practical. Error correction requires frequent, rapid measurement of qubits, real-time classical processing to interpret those measurements, and immediate feedback to apply corrections. This means that building a useful quantum computer is as much about the classical control systems as it is about the qubits themselves. The control hardware must be able to process vast amounts of information with near zero latency, all while interfacing with a machine sitting at cryogenic temperatures or inside a vacuum chamber. Engineering this hybrid system is one of the hardest tasks in modern computing. Error correction also interacts with hardware choice. Superconducting qubits with their fast gates are attractive for implementing surface codes because corrections can be applied quickly. Trapped ions with their long coherence times may need fewer corrections in the first place. Photonic systems can potentially exploit bosonic codes more naturally. Neutral atom systems may allow new kinds of geometric error correction codes because of their grid-like layouts. Each platform has to find a way to integrate error correction into its architecture, and the trade-offs differ. For investors and the public, error correction is often the most misunderstood part of the field. Press releases often highlight raw qubit counts, 50 qubits, 100 qubits, 400 qubits, but without error correction, those numbers are misleading. A 400 qubit machine with no error correction may not be any more useful than a 20 qubit machine, because errors accumulate too quickly to run meaningful algorithms. The real milestone is not just scaling up the number of qubits, but scaling up with error correction. The companies that succeed here will separate themselves from the pack. The timeline for achieving robust error correction is uncertain. Some optimists believe break-even logical qubits will be standard within 5 years. Others caution that scaling to millions of physical qubits for practical error-corrected machines could take decades. What is clear is that without error correction, quantum computers will remain in the domain of noisy, intermediate-scale quantum devices. These machines can perform experiments, explore algorithms, and demonstrate quantum effects, but they are unlikely to revolutionize industries without error correction. The stakes are enormous. With error correction, quantum computers could tackle problems in chemistry, optimization, and cryptography that are truly beyond classical machines. Without it, the technology may plateau, useful only in niche cases. This is why so much of the industry's focus is on error rates, gate fidelities, and the progress of logical qubit demonstrations. Every incremental improvement in coherence time or gate quality directly reduces the overhead required for error correction, bringing practical systems closer. Error correction also shapes the business strategies of quantum companies. IBM emphasizes its steady reduction in error rates and its roadmaps for implementing surface codes. Google highlights its progress toward logical qubits and break-even thresholds. IonQ emphasizes the quality of its trapped ion qubits as a foundation for efficient error correction. PsiQuantum argues that its photonic platform can achieve fault tolerance at scale by design. Microsoft bets that topological qubits, if they ever materialize, could avoid much of the error correction overhead altogether. Each of these narratives is built around the central role of error correction. In many ways, error correction is the ultimate bottleneck. It is the bridge between today's noisy prototypes and tomorrow's fault-tolerant machines. It is also a reminder that quantum computing is not just a physics problem, but an information theory and engineering problem as well. The field will not advance simply by adding more qubits. It will advance when those qubits can work together reliably, protected against the relentless noise of the quantum world. That is why the progress of error correction is watched so closely, and why it is likely to remain the defining challenge for years, perhaps decades, to come. Part 8. Noise and Decoherence. When people hear about quantum computers, the first question that often comes to mind is simple. What will they actually do? For most of the public, the phrase quantum computing sounds futuristic and powerful, but vague. The truth is that quantum computers are not just faster computers. They are designed to tackle certain classes of problems that are practically impossible for classical machines, even the most powerful supercomputers, to solve. The excitement around the field comes not just from the physics of qubits, but from the algorithms that show how this strange new hardware could transform science, industry, and security. The story of quantum algorithms begins with Shor's algorithm. In 1994, Peter Shor, a mathematician at Bell Labs, introduced an algorithm that could factor large numbers exponentially faster than classical algorithms. To understand why this was such a shock, it helps to recall how modern cryptography works. Systems like RSA, which secure much of the world's internet traffic, banking, and communications, rely on the fact that factoring a very large number into its prime components is extremely hard for classical computers. A 2048-bit number, for example, would take even the fastest supercomputers billions of years to factor by brute force. Shor showed that a quantum computer with enough qubits could do it in a matter of hours or less. The algorithm didn't just make headlines in mathematics. It alarmed governments and security experts worldwide. If large-scale quantum computers ever became a reality, much of the encryption that protects our digital world could be broken. Another milestone algorithm was Grover's algorithm, developed in 1996 by Love Grover at Bell Labs. Unlike Shor's exponential speedup, Grover's algorithm offered a quadratic speedup, which is less dramatic but still profound. It applies to unstructured search problems, where the task is to find a needle in a haystack. For a classical computer, searching n items takes n steps in the worst case. Grover showed that a quantum computer could do it in roughly square root of n steps. This meant that for certain optimization and search problems, quantum computers could deliver a meaningful advantage, even if it wasn't world-shattering like Shor's breakthrough. Grover's algorithm also had implications for cryptography. It could reduce the effective security of symmetric key encryption like AES by having the key length needed to brute force it. Since Shor and Grover, researchers have developed many more algorithms that exploit quantum mechanics. Some are highly specialized, like the Haro-Hasidim-Lloyd IEHHL algorithm, which solves certain systems of linear equations exponentially faster than classical methods. Others are more general, like algorithms for quantum simulation. Richard Feynman, one of the first to propose quantum computers in the 1980s, pointed out that simulating quantum systems, molecules, materials, chemical reactions, was essentially impossible for classical computers because the state space grows exponentially with the number of particles. A quantum computer, he argued, could simulate quantum systems naturally. This insight is still considered one of the most promising applications of quantum computing, designing new drugs, catalysts, and materials at the atomic level. Optimization is another major application area. Many industries face problems that involve optimizing across vast numbers of possibilities, finding the most efficient delivery routes for thousands of trucks, allocating resources in finance, or minimizing energy usage in a power grid. Classical algorithms struggle when the problem size explodes, but quantum algorithms may be able to explore the solution space more effectively using quantum parallelism and interference. Companies like D-Wave have focused on this area with their quantum annealers, while gate-based quantum algorithms like the Quantum Approximate Optimization Algorithm, QAOA, also target these problems. Machine learning has become another hot area for quantum applications. Quantum machine learning algorithms promise to speed up tasks like data classification, clustering, and optimization of neural networks. While it is still unclear exactly where the advantage will be most pronounced, the overlap between quantum computing and AI has attracted intense interest from both academia and industry. Frameworks like Xanadu's PennyLane integrate quantum circuits with machine learning libraries, allowing researchers to experiment with hybrid quantum classical models. Some proposals suggest that quantum systems could handle certain high-dimensional data representations more efficiently than classical systems. It is important to note that many of these algorithms are theoretical. They assume fault-tolerant quantum computers with thousands or millions of logical qubits, which we do not yet have. This is where the concept of the NISQ era, noisy intermediate-scale quantum, comes in. Coined by John Preskill in 2018, the term describes our current generation of quantum machines, which have tens or hundreds of noisy qubits. In the NISQ era, researchers are exploring whether useful algorithms can be run without full error correction. Variational quantum algorithms, like the Variational Quantum Eigensolver, VQE, are designed with this in mind. VQE combines quantum circuits with classical optimization to approximate solutions to problems in chemistry and physics. It has been tested on small molecules like hydrogen and lithium hydride, giving a glimpse of what may be possible at larger scales. The race now is to move from theory to practice. Companies and academic labs are benchmarking their hardware by running versions of Shor's, Grover's, VQE, and QAOA on available devices. For now, these demonstrations are small, factoring 21 into 3 and 7, or simulating simple molecules, but they prove that the algorithms are real and can run on real machines. The hope is that as error correction improves and qubit counts rise, these algorithms will begin to outperform classical methods on meaningful problems. One particularly interesting question is whether there are killer apps for quantum computers that we haven't yet discovered. Just as no one predicted in the 1940s that digital computers would eventually power the internet, social media, and smartphones, it is possible that the most important quantum algorithms have not yet been invented. This uncertainty is both a challenge and an opportunity. Researchers must balance working on known promising algorithms with exploring entirely new directions. Governments and corporations are especially interested in the cryptographic implications. If large-scale quantum computers become reality, much of today's public key infrastructure would be obsolete. This has spurred the field of post-quantum cryptography, which seeks to develop classical encryption methods that resist quantum attacks. The U.S. National Institute of Standards and Technology, NIST, is already standardizing new algorithms to prepare for a post-quantum future. This highlights how seriously Shor's algorithm is taken. Even though no machine capable of breaking RSA exists today, governments and businesses are already preparing for that possibility. At the same time, industries like pharmaceuticals, finance, energy, and aerospace are funding research into quantum algorithms for their own use cases. The dream is that quantum computers will allow them to design better drugs faster, optimize investment strategies more effectively, develop lighter and stronger materials, or make energy grids more efficient. Even if full-scale fault tolerance is decades away, these companies want to be ready. They are training talent, building partnerships, and experimenting with small-scale quantum algorithms today so that they can take advantage when the technology matures. The key to understanding quantum algorithms is that they are not about doing everything faster. A quantum computer will not make word processing, video games, or browsing the internet any quicker. Instead, it will make certain intractable problems tractable. These are problems where the number of possibilities explodes so rapidly that classical methods hit a wall, but quantum parallelism can keep pace. That is why quantum algorithms are both exciting and specialized. They are not about replacing classical computers, but about complementing them, tackling problems that classical machines cannot. In this sense, the promise of quantum algorithms is profound but realistic. They will not transform every corner of computing, but in the areas where they apply: cryptography, chemistry, optimization, and possibly machine learning. They could reshape industries. Just as the invention of digital computing opened up entirely new fields, the invention of practical quantum algorithms could open doors we don't yet know exist. The challenge, as always, is turning the theory into practice, and that depends on the slow, difficult work of building fault-tolerant hardware, improving error correction, and scaling up qubits. Until then, quantum algorithms remain both a beacon of what's possible and a reminder of how far there is to go. Part 9, NISQ Era. The current stage of quantum computing is often described with one acronym, NISQ, short for your Noisy Intermediate Scale Quantum. Coined by physicist John Preskill in 2018, the term captures both the promise and the limitation of today's machines. They are intermediate scale because they have more qubits than the earliest prototypes, dozens, sometimes hundreds, but far fewer than the millions needed for error-corrected, fault-tolerant systems. They are noisy because their qubits are unstable, decoherence times are short, and error rates remain stubbornly high. NISQ devices are not toys, but they are not yet the revolutionary tools quantum advocates envision. Instead, they occupy a gray zone where researchers experiment, explore, and search for usefulness amid the noise. To understand what NISQ machines can do, it helps to look at how they are built. A typical superconducting quantum processor, like those from IBM or Google, consists of a chip with tens or hundreds of qubits cooled to near absolute zero. Each qubit has control lines, readout mechanisms, and error mitigation routines. Running an algorithm involves sending microwave pulses to flip qubits, entangle them, and measure the results. In principle, these steps implement the same algorithms theorists developed decades ago. In practice, errors accumulate quickly. After only a few dozen operations, the results become unreliable. Trapped ion systems, like those from IonQ and Quantinuum, have fewer qubits but higher fidelity. Their operations are slower, but they can sometimes execute slightly deeper circuits before noise overwhelms the signal. This is the essence of the NISQ era. We can run real quantum algorithms, but only on small scales and with limited reliability. Factoring small numbers with Shor's algorithm is possible but trivial, numbers so small that classical computers solve them instantly. Running Grover's search is possible but only on toy databases. Variational algorithms like VQE and QAOA can approximate solutions to tiny chemistry or optimization problems, but the results are more proof of principle than practical utility. Researchers are excited to see theory meet hardware, but they acknowledge the gulf between current machines and those needed for transformative applications. Still, the NISQ era is not without value. One area of exploration is benchmarking. By running known problems on different hardware platforms, researchers can compare qubit quality, error rates, and algorithmic performance. This helps identify which architectures are progressing fastest and what trade-offs exist between speed, fidelity, and scalability. Benchmarks like quantum volume, introduced by IBM, attempt to capture not just qubit count but overall system performance. Quantum volume has become a widely cited metric, though not without controversy, since companies naturally prefer benchmarks that favor their own platforms. Another area of exploration is hybrid quantum classical algorithms. Recognizing that NISQ devices cannot run deep circuits reliably, researchers design algorithms that use quantum processors for specific subtasks while relying on classical computers for the heavy lifting. VQE is one example. The quantum machine prepares and measures quantum states, while a classical optimizer adjusts parameters iteratively. QAOA works similarly, with classical feedback guiding a quantum circuit toward an approximate solution. These hybrid algorithms are seen as the most likely path to near-term usefulness. They do not require fully error-corrected systems, but can still provide insights into chemistry, materials, science, or optimization problems if scaled carefully. Noise mitigation is another focus in the NISQ era. True error correction is not yet practical, but researchers have developed techniques to reduce the impact of noise without full fault tolerance. These include extrapolating results by intentionally increasing error rates and then mathematically estimating the zero noise limit, using symmetries in the problem to detect inconsistent results, and post-processing data to filter out noise. While these methods cannot substitute for full error correction, they can extend the reach of NISQ devices and make experiments more meaningful. For industry, the NISQ era is a delicate balancing act. On the one hand, companies must demonstrate progress to attract investment and maintain credibility. On the other, they must avoid overhyping machines that cannot yet deliver practical results. This has led to a wave of announcements about partnerships, small algorithmic demonstrations, and incremental improvements. IBM, for example, frequently announces increases in qubit counts and reductions in error rates, framing each as a step toward their long-term roadmap. IonQ highlights its qubit fidelity and modular scaling approach. Xanadu emphasizes integration with machine learning through Penny Lane. These messages are as much about managing perception as about technical milestones. The NISQ era has also sparked debate about whether near-term quantum advantage is possible at all. Some researchers argue that without error correction, the noise in current devices will always overwhelm any potential advantage. They suggest that meaningful quantum advantage may only arrive once fault tolerance is achieved, decades away. Others are more optimistic, believing that clever algorithms and hybrid approaches will uncover niches where NISQ devices can outperform classical machines sooner. These debates reflect the uncertainty of the field. No one knows for sure when or even if NASC machines will find killer applications. Nevertheless, the NISQ era is invaluable for training talent and building ecosystems. Universities, startups, and corporations are learning how to program quantum devices, how to design algorithms for real hardware, and how to integrate quantum processors with classical infrastructure. These lessons will pay off even if current machines never achieve practical utility. The skills, software frameworks, and experimental methods developed now will form the foundation for the fault-tolerant era to come. In this sense, the NISQ era is not wasted time but essential preparation. Another way to think about NISQ devices is as laboratories. They allow researchers to test theories about quantum information, to explore the physics of qubit interactions, and to refine control systems. Even if they never solve industrial-scale problems, they generate scientific knowledge. In chemistry, for example, experiments on small molecules help validate quantum algorithms against classical methods. In physics, NISQ devices are used to simulate toy models of quantum systems, providing insights into phenomena like magnetism or phase transitions. These applications may not revolutionize industries, but they advance science in meaningful ways. The limits of the NISQ era are clear, however. Without error correction, noise scales with the size of the system. Adding more qubits doesn't necessarily mean more power if the errors grow faster than the capacity to correct them. This is why announcements of 100 qubit or 400 qubit devices must be taken with caution. Raw numbers do not tell the full story. What matters is the effective number of qubits that can be used in a reliable computation. Often, that number is far smaller than the total qubits on the chip. In many ways, the NISQ era resembles the early days of classical computing. The first digital computers of the 1940s were noisy, unreliable, and limited. They could only perform specific calculations under careful supervision. But those machines trained the first programmers, inspired new algorithms, and pushed hardware forward. Similarly, today's NISQ devices may be crude compared to the vision of million-qubit machines, but they are the stepping stones that will eventually make those visions real. The NISQ era may last longer than some expect. Building fault-tolerant machines is an enormous challenge, and intermediate devices may dominate the landscape for another decade or more. During this time, the focus will be on extracting as much value as possible from noisy qubits, developing hybrid algorithms, and preparing the talent and infrastructure needed for the future. While some may be disappointed by the limitations, others see this as an exciting time, the chance to explore, experiment, and shape the foundation of a new field. Part 10, IBM Roadmap. Few questions in quantum computing attract as much attention, controversy, and frustration as the timeline question. When will practical, fault-tolerant quantum computers actually arrive? Investors ask it before they decide whether to put money into startups. Governments ask it before committing billions to national quantum programs. Companies in finance, pharmaceuticals, and energy ask it before allocating resources to pilot projects. And the public asks it simply out of curiosity, because headlines often imply that quantum computing is either just around the corner or forever stuck in the lab. The truth lies somewhere in between, and the uncertainty itself is part of what makes the field so fascinating. To start, it's important to distinguish between quantum advantage and fault tolerance. Quantum advantage refers to the moment when a quantum device can perform a useful task better than any classical computer. This could be achieved with noisy intermediate-scale quantum NISQ machines if clever algorithms and error mitigation strategies succeed. Fault tolerance, on the other hand, refers to the ability to run arbitrarily long quantum computations reliably, thanks to full error correction. Fault-tolerant machines are the ultimate goal, because they would unlock algorithms like Shor's for breaking encryption or complex simulations of molecules for drug design. Most experts agree that fault-tolerant systems will require millions of physical qubits, and that is decades away. But whether useful quantum advantage arrives sooner is still an open question. Predictions from leading companies vary widely. IBM has published detailed roadmaps extending into the late 2020s, with milestones like achieving thousands of qubits, implementing logical qubits with error correction, and building modular systems to scale further. Google has been more aggressive, with executives publicly stating that they aim to have a fault-tolerant machine by the end of this decade. IonQ has also made ambitious claims, projecting that its trapped ion systems could solve meaningful chemistry problems within the next few years. PsiQuantum, with its photonic approach, has insisted that it can build a 1,000,000-qubit machine within the 2020s, though it has yet to release concrete demonstrations. Microsoft, betting on topological qubits, has been more cautious, suggesting that while the timeline is long, their approach could ultimately leapfrog others if it works. The academic community tends to be more conservative. Many researchers emphasize that scaling from today's tens or hundreds of qubits to millions is not just a matter of engineering, but of solving fundamental challenges in materials science, cryogenics, error correction, and control electronics. They argue that the timeline for fault-tolerant quantum computing is likely measured in decades, not years. Some compare it to the development of nuclear fusion, always promising, always just out of reach, but still advancing steadily. That said, there are reasons to believe progress could accelerate. In the past decade, coherence times, gate fidelities, and qubit counts have improved dramatically. Error rates that were once measured in percentages are now measured in parts per thousand or even parts per 10,000. Logical qubit experiments, like those reported by Google and others, show that the concept of error correction is working in practice. Advances in cryogenic engineering, laser stability, and semiconductor fabrication are also pushing the boundaries. In short, the pace of improvement is real, even if the final destination is far away. The timeline also depends on what we mean by useful. For example, a quantum computer that can simulate small molecules more accurately than classical methods could already have value for drug discovery, even if it has only a few hundred logical qubits. Similarly, a quantum device that can optimize certain logistics problems faster than classical algorithms might save companies money, even if it cannot run Shor's algorithm. These narrower definitions of usefulness could arrive in the 2020s or 2030s. Full-scale, fault-tolerant quantum computers capable of cracking encryption or simulating complex proteins may be further off, perhaps into the 2040s or beyond. Another factor influencing the timeline is money. Quantum computing has become a global competition, with governments pouring billions into research and companies raising huge sums from investors. This funding fuels talent pipelines, builds infrastructure, and accelerates experiments. It doesn't solve the hardest scientific problems directly, but it ensures that progress is steady rather than stalled. Countries like the United States, China, and members of the European Union all see quantum computing as a strategic priority, which means sustained investment is likely for decades. This reduces the risk that the field will collapse if short-term results disappoint. Of course, timelines are also shaped by hype cycles. In the early 2000s, quantum computing was often dismissed as a distant dream. By the late 2010s, after Google's quantum supremacy announcement, some headlines made it sound as though classical computers were about to be obsolete. Neither extreme was accurate. Today, the narrative has matured slightly, with most serious players acknowledging that we are still in the noisy, experimental stage. But the temptation to overpromise remains, especially for startups that depend on investor enthusiasm. When IonQ went public, for example, it presented projections suggesting near-term breakthroughs, which critics argued were unrealistic. PsiQuantum's 1,000,000-qubit promises have been met with similar skepticism. The danger is that if timelines are exaggerated and fail to materialize, the field could face a credibility crisis similar to the artificial intelligence winters of past decades. The most responsible approach is to treat timelines probabilistically rather than absolutely. Instead of asking, when will we have a quantum computer? It is better to ask, what are the chances we will have a useful quantum computer in 5 years, 10 years, 20 years? Some analysts suggest that the probability of useful quantum advantage in the next 5 years is modest, perhaps 10 to 20%, but rises significantly in the 10 to 20-year range. Fault-tolerant machines, by contrast, are often given timelines of 20 to 40 years. These are not hard numbers, but attempts to reflect the uncertainty of the field. It is also worth remembering that the arrival of practical quantum computing may not be a single moment. Instead, it may be a series of milestones: the first break-even logical qubit, the first demonstration of quantum advantage in chemistry, the first industrial application that saves money, the first government deployment for cryptanalysis. Each of these could be celebrated as the arrival of quantum computing, depending on one's perspective. The revolution may come not as a sudden leap, but as a gradual unfolding. In the end, the timeline question may be less about prediction and more about preparation. Governments are already transitioning to post-quantum cryptography to safeguard against the possibility that Shor's algorithm becomes practical sooner than expected. Pharmaceutical companies are building teams to learn quantum algorithms in anticipation of future breakthroughs. Investors are diversifying across different hardware approaches, betting that at least one will succeed. The exact year may be uncertain, but the momentum is strong enough that few are willing to ignore the possibility. For now, the safest answer to the timeline question is that useful quantum advantage could arrive in the next 1 or 2 decades, while fully fault-tolerant machines are likely further off. The uncertainty is frustrating, but it is also what makes the field so dynamic. Every new result, an increase in coherence time, a demonstration of error correction, a record-breaking simulation, has the potential to shift expectations. Quantum computing may not obey the kind of predictable roadmap we are used to in classical technology. It is a journey with unknown twists and turns, and the destination, whenever it arrives, could reshape the technological landscape of the 21st century. Part 11. Google's supremacy. Whenever a new technology emerges, the story is never just about science. It is also about money. Quantum computing is no exception. While the physics is fascinating and the algorithms are revolutionary, it is the business side that determines who builds the machines, who funds the research, and how quickly progress moves from lab demonstrations to industrial applications. In recent years, the financial landscape of quantum computing has become as complex as the technology itself, with startups going public, governments investing billions, and investors both excited and cautious. Understanding this business side helps explain why quantum computing is advancing the way it is, and why hype and reality are constantly in tension. The first wave of serious commercial investment in quantum computing began in the 2010s. Before then, the field was dominated by academic labs and government-funded research. D-Wave, a Canadian company founded in 1999, was one of the first to pursue a commercial path, focusing on quantum annealers rather than gate-based quantum computers. Although controversial in the scientific community, D-Wave attracted significant attention and investment, positioning itself as a pioneer. The real explosion of business interest came later, as companies like Google and IBM began making public demonstrations, and startups such as IonQ, Rigetti, Xanadu, and PsiQuantum entered the spotlight. By the early 2020s, quantum startups were no longer small niche players. Many went public through SPACs, or special purpose acquisition companies, which allowed them to raise large sums quickly by bypassing traditional IPO routes. IonQ, for example, went public in 2021 and saw its stock price surge as investors embraced the promise of trapped ion technology. Rigetti followed in 2022 with a SPAC merger, though its valuation fluctuated sharply afterward as technical milestones proved harder to hit than expected. These public listings reflected a new phase. Quantum computing was no longer just a research project, it was an asset class. Investors were betting not on immediate profits, but on the long-term payoff of building the next generation of computing. Alongside private capital, governments have played a crucial role. The United States launched its National Quantum Initiative in 2018, committing over $1 billion to research, education, and infrastructure. The European Union began its Quantum Flagship program, with similar scale and ambition. China has invested heavily in quantum technologies, including both computing and communication, viewing it as a matter of national security and technological leadership. Japan, Canada, and Australia have also made quantum a strategic priority. These investments not only fund academic research, but also support private companies, creating an ecosystem where public and private money fuel each other. Despite all this investment, profits remain elusive. Quantum startups do not make money from selling hardware in the way classical computer companies did. Instead, their business models rely on partnerships, research contracts, and cloud access. Companies like IBM and Amazon offer quantum computers through the cloud, allowing researchers and businesses to run experiments on real hardware. Startups often sign deals with pharmaceutical companies, financial firms, or logistics providers to explore potential applications. These deals bring in revenue, but they are small compared to the hundreds of millions spent on research and development. In this sense, quantum computing today resembles the biotech industry. Companies burn through money in the hope of a future breakthrough that will pay off. The financial markets reflect this uncertainty. When IonQ first went public, its valuation soared, driven by optimism about its potential. But as with many SPAC-listed companies, the hype cooled and the stock became volatile. Rigetti experienced a similar trajectory, at times losing significant market value as technical challenges mounted. PsiQuantum, despite not being public, has raised over $1 billion from investors, but it remains under pressure to prove that its ambitious photonic approach can deliver results. Infleqtion, formerly Cold Quanta, has attracted attention for its work on neutral atom systems and quantum sensors, expanding beyond computing to diversify its revenue streams. Investors watch all these companies closely, not just for scientific milestones, but for signs of business sustainability. The question of valuations looms large. Are quantum companies worth billions today, even though practical applications may be decades away? Some analysts draw comparisons to the dot-com bubble of the late 1990s, when internet startups were valued astronomically despite lacking profitable business models. Many of those companies collapsed, but a few, Amazon, Google, eBay, survived and went on to dominate the modern economy. The analogy suggests that while most quantum startups may fail, the survivors could become giants of the mid-21st century. The challenge for investors is identifying which companies are Amazon and which are pets.com. On the other hand, some argue that high valuations are justified because quantum computing is not just another technology, but potentially transformative. If a company builds the first fault-tolerant quantum computer, the payoff could be enormous. New drugs, new materials, new cryptography, and entire industries reshaped. In this view, betting on quantum startups today is like investing in semiconductor companies in the 1950s or internet companies in the early 1990s. The risks are high, but the upside is unprecedented. Governments, recognizing the strategic stakes, add further justification by ensuring that quantum research continues regardless of short-term financial performance. The business side of quantum computing is also shaped by partnerships and ecosystems. Few companies can build everything alone, so collaborations are common. IBM partners with universities and corporations through its quantum network. IonQ has signed deals with Hyundai and Airbus to explore applications in batteries and aerospace. Microsoft integrates quantum computing into its Azure cloud, offering hybrid workflows that combine quantum and classical computing. These partnerships provide credibility, attract talent, and bring in revenue. They also spread the risk. Even if quantum computers take decades to mature, the collaborations produce scientific insights and incremental advances that justify ongoing investment. Another element is talent. Quantum physicists, computer scientists, and engineers are in high demand, and companies compete fiercely for them. Salaries are rising, and startups often lure researchers with the promise of stock options, betting that a successful breakthrough will make them wealthy. This creates a virtuous cycle. Money attracts talent. Talent advances the technology. Progress attracts more money. But it also creates pressure. Companies must continually show progress to keep both investors and employees motivated. One of the most striking features of the business side is how it intertwines with hype. Press releases often highlight breakthroughs that, while scientifically interesting, do not necessarily translate into immediate utility. Announcing a 433 qubit device, for example, generates headlines, even if the effective number of usable qubits is far smaller, due to noise. Startups emphasize roadmaps that project rapid scaling, sometimes more optimistic than what experts outside the company believe. This hype serves a purpose. It sustains investor interest, attracts partnerships, and keeps the field in the public eye. But it also risks creating unrealistic expectations. If progress slows or promises fail to materialize, the backlash could trigger a quantum winter, where funding dries up and momentum stalls. At the same time, the quantum economy is already diversifying. Companies like Infleqtion are developing quantum sensors and clocks, which may reach markets sooner than full-scale quantum computers. Quantum communication, another branch of the field, is advancing in parallel, with China leading the way in building quantum-secure communication networks. These adjacent technologies provide revenue streams that help sustain companies while the harder problem of computing matures. They also illustrate that quantum is not just one thing, but an entire ecosystem of related technologies, each with its own timeline and business model. In the end, the business side of quantum computing is a story of promise, risk, and patience. Investors must weigh the possibility of transformative returns against the likelihood of long delays. Companies must balance hype with credibility, raising enough money to survive while not overpromising and disappointing. Governments must justify public spending by emphasizing national security and technological leadership, even when commercial profits are far off. And researchers must keep the focus on science while navigating the pressures of financial markets. The stakes are enormous. If quantum computing fulfills its promise, the companies that lead the way could be the defining corporations of the century. If it falls short, billions of dollars will have been invested in technologies that never reach maturity. For now, the money continues to flow, the experiments continue to advance, and the business narrative evolves alongside the scientific one. The quantum race is as much about boardrooms and stock markets as it is about laboratories and algorithms. Part 12. Microsoft's topological approach. Quantum computing is not just a scientific or commercial project, it is also a matter of national security. From the moment Peter Shor published his algorithm in 1994, intelligence agencies and defense planners realized that a large-scale quantum computer could break much of the cryptography that secures modern communications. Governments around the world began quietly funding research, not only to build their own machines, but also to prepare for a future where adversaries might have the capability first. What began as a mathematical curiosity quickly turned into a geopolitical issue, one that is shaping the way nations invest in technology and plan for cyber defense. At the heart of the security question is public key cryptography. Systems like RSA, Diffie-Hellman and elliptic curve cryptography protect everything from emails to bank transactions to classified government messages. Their security depends on the difficulty of certain mathematical problems, factoring large numbers, computing discrete logarithms, or solving elliptic curve equations. Classical computers struggle with these tasks when the numbers are large enough, which is why encryption keys have grown from hundreds to thousands of bits over the decades. Shor's algorithm showed that a sufficiently powerful quantum computer could crack all of these problems efficiently. In theory, this would render most of today's encryption obsolete. This possibility has triggered what some call a quantum arms race. The United States, China, the European Union, and other nations have launched massive quantum initiatives, not only to push the science forward, but also to ensure they are not caught unprepared. China, in particular, has invested heavily in quantum technologies across the board: computing, communication, and sensing. It has already demonstrated a quantum communication satellite, Mikius, which enables secure key distribution using the principles of quantum mechanics. This has raised concerns in the West that China could leap ahead in certain areas, even if it lags in others. In the United States, agencies like the National Security Agency, NSA, and the National Institute of Standards and Technology, NIST, have been working to transition to post-quantum cryptography. The idea is to develop new encryption schemes that remain secure even against quantum attacks. These schemes are based on mathematical problems believed to be hard for both classical and quantum computers, such as lattice-based cryptography. In 2016, NIST launched a global competition to standardize post-quantum algorithms. After years of submissions and analysis, it announced a set of finalists in 2022, which are now being prepared for adoption. This proactive approach is meant to ensure that when large-scale quantum computers eventually arrive, the world's communications will not suddenly become vulnerable. But there is another, more immediate concern: harvest now, decrypt later. Adversaries could already be intercepting and storing encrypted communications, waiting for the day when quantum computers are powerful enough to crack them. If that happens, decades of past secrets could be revealed at once. This has added urgency to the adoption of post-quantum cryptography. It is not enough to protect only future messages. Sensitive data transmitted today must also be safeguarded against eventual decryption. Governments and corporations alike are beginning to consider the lifespan of their data when planning encryption strategies. The military implications go beyond encryption. Quantum computers could give advantages in areas like code breaking, secure communications, and advanced simulations. For example, being able to simulate materials or chemicals at the quantum level could help design new stealth technologies, explosives, or energy systems. Quantum optimization algorithms might improve logistics for troop movements or supply chains. Even quantum sensors, technologies related to but distinct from computing, could allow for navigation without GPS or detection of submarines underwater. These possibilities explain why defense departments view quantum technologies as part of their strategic priorities. The quantum arms race is also shaped by alliances. The United States and its allies coordinate through programs like the National Quantum Initiative and joint projects with the European Union, Canada, and Australia. China, meanwhile, pursues a more centralized, state-driven approach, with large government labs leading the effort. Both sides emphasize talent recruitment, infrastructure building, and integration with industry. The competition is not just about who builds the first fault-tolerant quantum computer, but also about who develops the supporting ecosystem of algorithms, applications, and trained professionals. Critics warn, however, that framing quantum computing as an arms race could distort priorities. Unlike nuclear weapons, where possession by one nation can directly threaten another, quantum computers are more like general-purpose tools. Their benefits extend to medicine, energy, and finance, not just military use. Overemphasizing the security threat could encourage secrecy at the expense of open scientific collaboration, slowing down overall progress. Many leading quantum researchers argue that the field has advanced as quickly as it has precisely because it has been open, with ideas shared across borders and disciplines. Turning it into a tightly controlled military competition could reduce this collaborative spirit. Yet some level of secrecy is already inevitable. Defense agencies are unlikely to broadcast every advance they fund, and companies working on cryptography often keep results confidential. The balance between openness and security will be delicate. Too much openness risks adversaries exploiting breakthroughs, but too much secrecy risks slowing down progress and duplicating effort. For now, most of the field remains open, but classified research is almost certainly taking place in parallel. For businesses, the national security angle creates both risks and opportunities. On the one hand, the possibility that quantum computers could break encryption means companies must prepare to transition to post-quantum cryptography sooner rather than later. On the other hand, governments are offering large contracts and grants for companies that can contribute to secure quantum communication, cryptography, or computing. This makes defense a major customer for quantum startups, providing funding streams that can help them survive while waiting for commercial applications to mature. The narrative of the quantum arms race also plays a role in sustaining hype. Politicians and defense officials often frame quantum as a matter of national survival, comparing it to the space race of the Cold War. This rhetoric helps justify billions in spending and ensures that research programs remain politically popular. But it can also raise public expectations unrealistically, suggesting that a quantum breakthrough is imminent and will reshape global security overnight. The reality is slower and more incremental. Progress will come, but not in the form of sudden leaps that make today's encryption vanish instantly. In the long run, the outcome of the quantum arms race may not be a single winner, but a world where multiple countries have access to fault-tolerant quantum computers. The balance of power will then depend on who adopts post-quantum cryptography in time, who trains the best talent, and who builds the strongest application ecosystems. Just as classical computing became a global technology with contributions from many nations, quantum computing is likely to follow a similar path. What is different is the degree to which security is tied to the outcome. Whoever lags in adopting new cryptography could find their secrets exposed. Ultimately, national security concerns are both a driver and a constraint on quantum computing. They drive funding, talent recruitment, and urgency, but they also impose secrecy, hype, and pressure. The cryptographic threat ensures that governments will never ignore the field, even if commercial applications are slow to arrive. And the strategic potential ensures that the race will remain global and competitive for decades. Quantum computing is not just about physics or algorithms or profits. It is also about geopolitics, trust, and the future of secure communication in a digital world. Part 13, Rigetti. When most people hear the term quantum computer, they imagine some kind of futuristic machine, glowing with blue light and humming with energy. In reality, there is no single blueprint for what a quantum computer should look like. Instead, several radically different approaches are being pursued, each with its own strengths, weaknesses, and philosophical bets about the best path forward. The diversity of approaches is both exciting and confusing. It means the field is less like a race with one track and more like a marathon where runners take different routes through uncharted terrain, hoping theirs will lead to the finish line first. The most widely used approach today is superconducting qubits. Companies like IBM, Google, and Rigetti have all focused on this architecture, which builds qubits from tiny superconducting circuits cooled to temperatures just a fraction of a degree above absolute zero. These qubits exploit the properties of superconductivity, where electrons flow without resistance and are controlled using microwave pulses. The advantage of superconducting qubits is that they can be manufactured using techniques borrowed from the semiconductor industry, making them relatively scalable. They also have fast gate times, meaning computations can be performed quickly. The drawbacks are equally significant. Coherence times are short, typically measured in microseconds, and errors accumulate rapidly. This means circuits must be shallow, limiting what can be done before noise overwhelms the computation. Another leading approach is trapped ion qubits, the specialty of companies like IonQ and Quantinuum. Here, instead of building artificial circuits, researchers trap individual charged atoms, ions, in electromagnetic fields. Lasers are used to manipulate their quantum states and entangle them. Trapped ions have the advantage of being nearly identical qubits. Every calcium or ytterbium ion is the same, which makes for excellent consistency. They also have much longer coherence times than superconducting qubits, often lasting seconds instead of microseconds. The trade-off is speed. Ion operations are slower than those of superconducting qubits, and scaling up to large numbers of ions is a technical challenge. Nevertheless, trapped ions are often praised for their accuracy and potential for modular architectures. Photonic qubits take a very different approach. Companies like PsiQuantum and Xanadu are betting on photons, particles of light, as the carriers of quantum information. Photons are attractive because they interact weakly with their environment, which means they have long coherence times and are naturally suited for communication. They also work at room temperature, eliminating the need for massive dilution refrigerators. The challenge is that photons are hard to control and detect. Entangling them requires clever schemes involving beam splitters, interferometers, and probabilistic gates. PsiQuantum is pursuing a path that involves building massive arrays of photonic circuits on silicon chips, while Xanadu develops continuous variable photonics with devices like squeezed light sources. The vision is that photonic qubits could scale to millions more easily than other architectures, though practical demonstrations are still limited. Neutral atom qubits represent another promising frontier. Companies like Infleqtion, formerly Cold Quanta, and Quera, are developing systems that trap neutral atoms, atoms with no net charge, using arrays of lasers. These atoms can be arranged in 2 or 3-dimensional grids, forming large qubit arrays. The atoms themselves are stable, and entanglement can be created by exciting them into Rydberg states, where their electrons are far from the nucleus and highly sensitive to interactions. Neutral atom systems combine some of the advantages of trapped ions, long coherence, uniform qubits, with the potential to scale into large arrays. They are also reconfigurable. Lasers can move atoms around dynamically, creating flexible circuit layouts. The field is newer than superconducting or ion-based approaches, but it has gained momentum in recent years. Then there are topological qubits, the approach championed by Microsoft. Topological qubits are not based on particles we can directly manipulate, but on exotic states of matter, where information is stored in the global properties of a system rather than in local states. The idea is that these qubits would be inherently protected against noise, solving the problem of error correction at the hardware level. In practice, realizing topological qubits requires creating and controlling quasi-particles like Majorana zero modes, which remain controversial and extremely difficult to detect. Microsoft has spent years pursuing this path, facing skepticism from the wider community due to delays and lack of clear experimental confirmation. If it works, topological qubits could be a game changer, but for now, they remain largely theoretical. Each of these approaches reflects a different balance of trade-offs. Superconducting qubits offer speed and industrial know-how, but suffer from noise. Trapped ions offer precision and stability, but struggle with scaling. Photonics offers scalability and communication advantages, but faces daunting technical hurdles in creating reliable gates. Neutral atoms offer flexibility and potential for massive arrays, but are still in the early stages of proving their robustness. Topological qubits promise fault tolerance at the hardware level, but remain speculative. None of these paths has yet emerged as the clear winner, which is why so many companies and research labs continue to hedge their bets. The diversity of approaches also reflects the uncertainty of the timeline. If superconducting qubits can be scaled quickly with improved error correction, they might dominate the near term. If photonic systems succeed in mass integration, they might leapfrog others in the long run. Neutral atoms could quietly grow into a scalable architecture if their reconfigurable grids prove reliable. Trapped ions might find a niche in applications requiring extreme precision. Topological qubits, if ever demonstrated, could reset the entire field. The competition is less like a race to a single finish line and more like an evolving ecosystem, where different species of quantum machines may coexist and serve different purposes. Another interesting angle is how these approaches intersect with national strategies and business models. IBM and Google, with superconducting qubits, benefit from their integration with massive classical computing infrastructures and cloud services. IonQ and Quantinuum, with trapped ions, present themselves as providers of the highest fidelity qubits available today. PsiQuantum, with its photonic bet, attracts investors who are willing to gamble on a longer term but potentially more scalable future. Infleqtion and Quera highlight their diversification into sensors and neutral atom platforms beyond computing. Microsoft's topological quest fits with its identity as a long-term, software-driven company, willing to take risks that may only pay off decades from now. What is remarkable is that despite their differences, all these approaches are advancing in parallel. This creates a rich, competitive environment where breakthroughs in one architecture often inspire ideas in others. For example, error mitigation techniques developed for superconducting qubits can sometimes be adapted to ions or atoms. Photonic approaches to communication may eventually integrate with ion-based processors. Hybrid systems are even being explored, where different types of qubits handle different tasks. The field is not just a competition, but also a dialogue between different visions of what a quantum computer should be. In the end, the story of quantum hardware is one of diversity and uncertainty. There may not be a single right answer. Just as classical computing evolved into a landscape where CPUs, GPUs, and specialized chips coexist, quantum computing may evolve into a world where superconducting processors, ion traps, photonic systems, and neutral atom arrays each play a role. The next decade will reveal whether one architecture pulls ahead decisively or whether the future of quantum will be pluralistic. What is certain is that the hardware race is as important as the algorithms and the business strategies. Without stable, scalable qubits, even the best ideas remain theoretical. With them, the quantum revolution can finally leave the lab and enter the real world.